In this video, we're gonna talk about Takagi's generalization of the notion of conductor. Let us first review the definition of a conductor of a finite abelian extension K of Q. Recall that by Chronicle Weber, any such extension must lie inside some cyclotomic extension of Q. Now we then define the conductor of K over Q to be the smallest integer m such that Q is contained inside the m cyclotomic field. One important property of the conductor is that it governs ramification in K. To be more precise, a Q prime P is ramified in K if and only if P divides the conductor of K over Q. To talk about Takagi's generalization of conductor, we first need to review Takagi's generalization of Chronicle Weber. For every number field K and a modulus m of K, Takagi defined the ray class field corresponding to the modulus m of K to be the class field for Pm. This is a generalization of cyclotomic fields. Then it turns out that every finite abelian extension of K is gonna be contained inside some ray class field. The reason was because every finite abelian extension of K is gonna be the class field of some ideal group H. Now since H contains Pm, L must be contained inside the class field of Pm, which is a ray class field. Now, imitating the definition of conductor in the case of a finite abelian extension L of Q. For a finite abelian extension L of a number field K, we can define the conductor of L over K to be the smallest modulus m such that L is contained inside the ray class field corresponding to m. Now, what do we mean by smallest? What does it mean to say that one modulus is smaller than another one? Recall that a modulus is just a product of prime ideals, both finite and infinite. Thus, we can talk about a modulus dividing another one. And if the modulus m divides the modulus m prime, then we say that m is less than or equal to m prime. Therefore, by definition, the conductor of L over K must divide all m such that L is contained inside the ray class field corresponding to m. Any modulus m satisfying this property is called an admissible modulus of the extension L over K. In this terminology, our previous discussion can be rephrased as follows. So the conductor should divide all admissible modulus of L over K. In other words, it's the least admissible modulus of L over K. Now it turns out that the converse is also true. That is, if the conductor of L over K divides the modulus m, then actually m is an admissible modulus of L over K. More generally, if a modulus m prime is divisible by some admissible modulus m, then m prime itself must be admissible. To see why this is the case, we need another characterization of admissible modulus. Observe that if m is an admissible modulus of L, then L is the class field of some ideal group H with modulus m. And conversely, if L is the class field of some ideal group H corresponding to some modulus m, then L lies inside the ray class field corresponding to m. Now, L is the class field of some ideal group with modulus m if and only if the degree of L over K is gonna be equal to the index of the norm subgroup of L over K corresponding to the modulus m inside Im. We can thus use this to give another characterization of admissible modulus. That is, a modulus m is admissible if and only if the index of the norm subgroup of L over K with respect to m inside Im is equal to the degree of L over K. Now, coming back to our statement, let's say that m is an admissible modulus and m divides m prime. Let's see why that would mean that m prime is admissible. Well, so for M to be admissible, that's equivalent to saying that the index of HM inside IM is equal to the degree of L over K. On the other hand, since M divides M prime, we must have that the natural math from IM prime quotient out by HM prime to IM quotient out by HM is onto. Therefore, the index of HM inside IM must be less than or equal to the index of HM prime inside IM prime. And thus, the degree of L over K must be less than or equal to the index of HM prime inside IM prime. But now, recall that previously we have established that for any norm subgroup associated to any modulus M prime, we should have that the index of HM prime inside IM prime should be less than or equal to the degree of L over K. This comes from Weber's generalization of Dirichlet's theorem. Thus, combining this with the inequality that we just established, we get that the index of HM prime inside IM prime is going to be equal to the degree of L over K, and thus M prime is an admissible modulus. Thus we have shown that any modulus M prime that is divisible by an admissible modulus M must itself be admissible. In particular, we see that if a modulus M is divisible by the conductor, then it itself must be admissible. And thus we have the conductor of L over K divides the modulus M if and only if the modulus M is an admissible modulus of L over K. Up next, we are going to talk about the relationship between conductor and ramification, and more generally, the relationship between the conductor and the discriminant.